So that summarizes some of the recent work that we've been doing within Cargill to try and better understand how de-icers perform and how to measure their performance. I will give you a brief recap of the main points that we talked about. So what we said was, first of all, it's important to distinguish between ice melting capacity, the total amount of ice that a chemical can melt, and the ice melting rate. They're important because if we've got a situation, so for example, if we assume that salt is ineffective at -4 because it doesn't work after 1 hour, that's fine as long as we know we need it to work in 1 hour. But if we've got a situation where time is available, given enough time, salt has a lot of ice melting capacity as cold as all the way down to its eutectic temperature. We talked about how the standard SHRP test suffers from some imprecision and some inaccuracies, and that it can underestimate ice melting capacities. We saw that we can improve both the precision and the accuracy of the test by using higher application rates in the test and by making measurements over a long enough period of time that we give the chemical enough time to do all of its melting action. We saw that salt has got a large amount of ice melting capacity, all the way down to its eutectic temperature, so even to below 0. We saw that the ineffectiveness of salt at cold temperatures, as long as we're above the eutectic, as long as we're above -6, is due to a slow ice melting rate, not low ice melting capacity. We talked about how ice melting capacity is carved in stone. It is a constant that's characteristic of the chemical and cannot be changed. But we also saw that rate is not carved in stone. We saw that we can manipulate rate and we can make it faster by changing the composition of the system. And so this opens the possibility of activating salt at colder temperatures. And one of the ways that we currently do that is with pre-wetting. We saw pre-wetting with salt with liquid mag chloride. The same thing is true with calcium chloride. I didn't talk about calcium chloride, but the same thing occurs. That significantly increases the ice melting rate of salt at temperatures as low as -4 Fahrenheit. We saw that if we're using hot mixes, that if we pre-wet salt with hot mixes, that there is a benefit that is over and above just the ice melting of the liquid itself. So it's not as simple as saying if you put 20% mag chloride in your hot mix, that you're going to get that additional melt from the 20% mag chloride and that's it. What we saw was that the brine itself is facilitating the dissolving and the diffusion of those sodium chloride ions onto the ice, and thereby increasing the ice melting rate. And so we saw that pre-wetting with hot mixes increases the ice melting rate of rock salt, and the more mag chloride or calcium chloride, the more you add, the greater the effect. We saw that we do not yet know what the optimum pre-wetting rates are. The way that I think about this is that the liquid enables the salt to talk to the ice. It's probably the case that the actual de-icing action's always happening from a brine. And you never truly have dry ice. Dry salt. Even bone-dry salt has got some layer of moisture on it, maybe only a few molecules thick. And it's always going to be this liquid brine layer that's probably most efficiently interacting with the ice surface to cause the ice to melt. We know that liquids melt ice enormously faster than dry salt does. So probably what's going on is that the brine is facilitating both the dissolving of the salt and the diffusion of the salt away from the salt crystal and onto the ice. And the trick is going to be figuring out what the optimum ratio of liquid to salt surface area to pavement surface area is to maximize that benefit. And I think we can do that with some tailored experiments. Now, finally, the last thing that we talked about was trying to better understand how de-icing liquids behave when they're exposed to continual freezing precipitation, and see if we could learn something about longevity. So we talked about how we could apply the modified version of the aircraft de-icer water spray endurance test to highway de-icers. We saw that depending on if a pavement is treated with a de-icing fluid or if it's dry, that it goes through different stages. That if the pavement has no chemical on it, when it's exposed to W-set freezing precipitation, we get immediate formation of this characteristic white snow-like rime ice. But if there's a deicer present, the pavement goes through a series of stages. Initially, we form a layer of melt on the surface. This melt layer increases and is diluted over time as more freezing precipitation occurs, until it's diluted to a point where it starts forming an initial phase of a translucent, non-adherent, fragile, weak glaze ice. That phase will continue for a period of time, and then there will be a transition when we start seeing that white rime ice forming. And it raises the interesting question of whether the transition to the white rime ice might be some relative indication of how long different chemicals would have some effectiveness on the road. We saw that there are certain additives, in particular some high molecular weight polymers, that appear to increase the length of time that these deicer fluids will resist the transition to the white rime ice over time. And next steps, if interesting, would be for the industry to explore how this predicts chemical longevity under field conditions. So that takes me exactly to 50 minutes, which was my allotted time. I will be around all day today at the Cargill booth. I'd be very happy to answer questions at any time during today. And I guess if you want to, I can field any questions you have right now, if there's any quick questions. All right then, thank you very much for your attention.